The highland suites on the moon are extremely important. They provide a idea of the early evolution of the moon and set some time limits with regards to how the early moon evolves. But they are loaded with pitfalls in terms of interpretation. This There we go. This slide is just a slide that just really illustrates one way of illustrating the compositional variation, the relationship between among these different lithologies, the ferronorthocytes, the magnesium suite, the alkali suite, and some of the more evolved lithologies. And what I did plot here is essentially all the mineralogical chemical data that have been produced for these lithologies since the early 1970s. And you can see there's a lot of variation in these, and a proper way of interpreting them is really needing to look really close at these, because in some cases, these really represent, mixtures of materials, impact related materials. And so one needs to really look closely at the petrology and then utilize that to establish the chronology, to establish some fundamental principles on their origin and evolution. There are a variety of models for the origin of, particularly I'm going to focus this upon the magnesium suite, the alkali suite, and the evolved lithologies on the moon. One is just simply a fractional crystallization model that you can see to your left, which is you have a parental magnesium suite magma that crystallizes, producing these whole suites. You have another model where you could potentially have a variety of episodes of magmatism producing this wide dispersion of lithologies. And then another alternative is that potentially you could have all of these essentially produced by impact processes, and these are products of crystallization of impact melt sheets. Now, what would be really key to making all of these, to examining these and establishing chronology and evolution, is essentially being to better understand these, is to look at the parental magmas for these. Unfortunately, all of these rocks are plutonic in nature, and it has long been a search for petrologists to look at magnesium suite parental magmas that are volcanic in origin. And we've found a number of rock types within 73001, 73002 that we think they represent melts, and this talk just essentially exhibits or shows some of the characteristics and comes to the conclusion that these rocks are truly volcanic and parental to the magnesium suite. We've done XCT imaging of the core, done mineral separates, pulled out interesting individual fragments, done SEM analyses, electron microprobe analyses of some of these lithologies, and then, of course, have done trace element analyses using laser ablation, ICP-MS, at the Johnson Space Center. This is really a cool fragment that we found, and it's very similar in overall characteristics to those identified by Chen et al. Or Yen et al. In a paper he just released. And this is kind of fantastic, in which you have very magnesium-rich olivines within a matrix of plagioclase, some glass, and some minor pyroxene. And you can see the magnesium compositions are extremely high and out of the compositional range that you commonly see in Mare basalts. This is just an image that illustrates some of the characteristics of this matrix. So again, you have olivine as the first phase, and that's followed by the crystallization of plagioclase, which kind of can partially mimics what you see in something like the magnesium suite. And if we just go ahead and plot this on this this diagram I showed you earlier, that's where the star plots. It plots this melt composition, whether it's impact or it's a magma derived from the interior, is a point that we'd like to make here. We've also calculated melt densities and melt viscosities, and this diagram just illustrates that this melt density, and it doesn't illustrate the viscosity, are far lower than the Mare basalts. And then what we did to better understand its origin, its relationship potentially to the magnesium suite, we've conducted a lot of laser ablation ICP analyses that are illustrated here, where we analyze the olivine and the matrix and put together a melt composition. This illustrates some of the trace element characteristics. And what you'll see here in the diagram to your left, this is nickel plotted against cobalt. And you can see, at least for the olivines, they tend to plot right near the olivines in the magnesium suite. So these tend to mimic, or at least be very similar to what one sees in the plutonic rocks representing the magnesium suite. Also, you can see I plotted the melt composition here, which is also very, very low in nickel and cobalt. And it is also low in siderophile elements, suggesting that this is probably not a product of impact, but probably truly a magma derived from the lunar interior. Also showed to the diagram to your right is that this diagram, the matrix and the bulk composition that we determined from this, does have a creepy-like signature that essentially mimics creep basalts, although somewhat lower. And then this is, I borrowed from Clive Neal in our chapter in New Views of the Moon 2, which just illustrates that there is some differences in these two ratios compared to the creep basalts. This just illustrates the creep basalts and the urcreep on the upper right-hand corner. Some of the data we have for the magnesium suite cumulates shown in the boxes, which maybe you're comparing apples with oranges here when you're comparing it to the basalts. But this illustrates also the melt composition, which is a bit different from the creep basalts. So in conclusion, what I'd like to just mention that these lithologies do not represent impact melts. They really represent magmas derived from the interior of the moon. Primarily, you can focus on the nickel and cobalt, but also the rare earth elements. These we think represent, volcanic equivalents to the and magmas of the magnesium suite. Although an age was derived from this at about 4.2, suggesting this is ancient. Clearly, there's a problem based on the philosophy that Lars and I have been using in dating plutonic rocks from the moon, that one needs to use multiple chronometers. So the age of this is probably older than 4.2, but it's ancient. And so let me just leave you with that. And this has really been a great rock to work on. But thank you very much.